Hi, I'm Mark Erickson. I've been working with computers for a very long time. I've performed many different roles throughout my career. Pretty heavily deep in the Microsoft stack, which frankly used to be kind of lame, but nowadays is kind of cool, largely due to Satya Nadella. I moved here in '03 for grad school and never left because Eugene is a vortex. I'm currently at Pacific Source Health Plans, and I'm focused on APIs, API development, management, security, what makes an API good, DevOps, Azure and on-prem hybrid infrastructure, and then development process improvement. And I'm here today to talk to you about foundational computer science theory. So this is what we're going to cover. There's a lot here. There's a lot of math here. We're going to be pretty loose and hand-wavy on that, and then we're going to focus more on kind of what you can take away from that and hopefully apply to your careers. This is really the foundational question. In computational theory, does P equal NP? I like to ask this of everybody I interview. In fact, there's some people in the room that I've asked this of in their interview process. We'll talk more about why I do that later. These are the main sources here. I swear these two books, Sipser's and The Introduction to Algorithms, it's most of a formal education in computer science. If you really did work through both of those books and understand everything in there, you probably skipped school. I want to give a shout out to Professor John Rager at Amherst College, Professor Eugene Lux here at the University of Oregon. They're the folks that actually taught me all this stuff. And then I have to give a shout out to Matt Ginsberg, who wrote Factor Man up there in the corner. He was my advisor in grad school and is one of the very few people I've ever encountered who believes that P does equal NP. And then there's a whole lot of gratuitous Wikipedia theft in here. Almost all the slides I just straight up stole. All the links point back to Wikipedia. The theory section in Wikipedia is surprisingly good. So yeah, math. There's a lot of math. All theory is really math. We are not going to cover all of that. I can't teach you two to 3 years of grad level math really quick. So gray-black slides, we're going to do a lot of hand waving. I want to show you what the math looks like so you have some idea of what it is. And then there's a whole bunch of links and you can follow those and go deeper if you so choose. Slides with backgrounds are much more focused on what's important and what you can hopefully take away. We start off with proofs. A lot of mathematical theory is based around proofs. In computer science, there's two main proofs we're concerned with, proofs by contradiction and proofs by induction. Proof by contradiction is pretty self-explanatory. You're trying to prove something, you assume it to be not true. You show that that assumption leads to a contradiction, and therefore you can conclude that the thing you assume to be not true is true. And you can use that to prove a lot of things, like Euclid's elements. If two angles of a triangle are equal, the opposite sides are equal. You can prove the infinitude of prime numbers, irrationality of square root of 2. And then we have proofs by induction. A lot of the loop invariant proofs in computer science, like how long this will run or will it run, are based on loop induction. So stuff like the sum of the natural numbers greater than 0 or equal to n over n plus 1 divided by 2. Fibonacci numbers, and then prime factorization. Every natural number greater than 1 is a product of one or more prime numbers. Prove that by induction. The halting problem. This is kind of the first major theoretical problem in computer science. The question is, does a program run forever or not? If you've done any recursive programming at all, you've probably accidentally run into this. And there's a fairly straightforward informal proof by contradiction. If we assume we had something that could solve this, you could very easily build a program that would use that to give you the converse result and prove that you can't do that. But to actually do it, you need a lot more math. The key bit here is that it's for all possible program input pairs. So like if you say you had a program that was like, while n is less than 100, add 1 to n. If you give it an n that's less than 100, it's going to run up to 100 and it's going to stop. If you go to n of 101 or greater, that's going to run forever, or at least until you run out of memory. So the key part here is all possible program input pairs. There we go. Machine models and grammars. This is definitely something to that you want to take away. Machine models are mathematical formulations of what a computing machine can do. There's a bunch of different ones, and they all kind of comprise automata theory. At the very bottom level, we have combinational logic, so just what you can do on a circuit board, no state, no memory at all. Then we have what's called a finite state automata that gives you state but no memory. And then we have a push-down automata, which gives you state plus an infinite stack, which you can't search at all. And then we have a Turing machine, which is infinite memory, truly infinite memory. Grammars are a way of expressing what we can solve. You generally have a set of possible inputs, and then you have a subset of those that are strings that you recognize, and that's called an acceptance state, and that's a solution to the problem. It's not unlike regex. The main takeaway here is the more powerful the memory we have, the more subsets of the possible input space we can recognize. So this is the starting point, finite state automaton. As mentioned, it doesn't have any memory, it only has states. Think of like a turnstile at a subway. Right? Like you put a coin in, that unlocks it, you turn it, that locks it again. Put another coin in, that unlocks it, you turn it, that locks it again. If you put a coin in while it's unlocked, well, it's just going to stay unlocked. Similarly, you can use this to recognize cardinality. So given an input string, are there an even number of zeros or an odd number of zeros? You can do that. But you can't do any really counting. Old school traffic lights that just go through the states, another similar example. Next up, we have push-down automata. Same thing, but now we have a stack. So when you have a stack, you actually have memory, but you can only read the top of it. You can't actually search through it. You only get the top. Back in the day, this kind of memory was much, much easier to build, when they had like vacuum tubes and room-sized computers, so this was important. Nowadays, it's not as much because that's not really how memory works, right? You can search through memory. But this also underpins why stacks are generally much more efficient to use for algorithms, so anytime you can use a stack or a heap or some other data structure that doesn't have a search, they're better, right? Faster. What's on? Right. All right, so now we get to the Turing machine. This is a computing machine with infinite memory and infinite time. This representation is capable of implementing any computer algorithm out there. There's a whole lot on here about that. This is what the math actually looks like. Again, we're webbing hands. You just got to trust me that works. So why do we call this the Turing machine? This guy, Mr. Alan Turing, absolute legend. He's kind of like Darwin to biology, or Isaac Newton to classic physics. This guy is the father of basically all of computer science. He proved the halting problem in 36. That's like 8 years before we had anything close to a computer. He designed a stored computer program before we could build it. He was part of the elite team of code breakers at Bletchley Park in the United Kingdom, and they worked on the German machine-based ciphers called the Enigma machines, which is how the Germans were sending messages between various parties in the war. Think like a decoder ring, but like much better, much more advanced than that. They were considered unbreakable at the time until this guy and his team broke it. And because of that, we were listening to the German messages for like the last 2 years of the war. And that makes him probably the largest contributor to the Allied victory. Like, D-Day probably wouldn't have worked without this. We certainly would have lost a lot more stuff to the subs in the Atlantic. He took the experience from here and excuse me, that team built Colossus, which is truly the world's first programmable digital computer. He was gay, and he was charged for obscene acts in 1952, and then chemically castrated, essentially forced hormonal treatment, and he killed himself 2 years later. There's subsequently been apologies, and now he's on the 50-note bill, but do better, humans. This guy also he formulated what's now called the Turing test, which has basically been the line for an AI for 70 years and was just finally beat essentially this year. The first legit pass is ChatGPT, the modern large learning models. There we go. So decidability and computability. Decidability is really close to the halting problem. Not quite, but it's, is there a way that we can come to a decidable and effective solution for deriving an answer to a given problem? Computability is, given a Turing machine, what can we solve? And that's, again, unlimited time, unlimited space. Okay, so now armed with all of that, we can actually talk about the halting problem again. This is a sketch of a rigorous proof of what that would look like. We're not going to go through that. Keep in mind, this is what Alan Turing proved in '36 before there were any computers, 90 years ago. The proof is very similar to Cantor's diagonal argument, which proves that there's way more real numbers than there are integers. The real numbers are uncountable. And you can use this to prove that there's way more unsolvable problems than there are solvable problems. It's interesting. All right, so now time and space complexity. This is where we kind of get to the nuts and bolts. This is how we measure the performance of an algorithm. It's algebraic in relation to the size of the input, which we call n. You can have n factorial, which is really, really bad, 2 to the n, which is exponential, polynomial n squared, n log n. Now we're starting to get to something reasonable, n, and then actually literal times. We have 3 different measures of bounds. Big O is the important one. That's worst case. Omega is a lower bound. Very rarely does that matter. And then theta is a tight bound. So for all inputs, it'll run within this tight, narrow bound. If you consider sorting algorithms, n is the number to sort, n is the number of things you're going to sort, and all the various sorting algorithms are expressed in some constant of n. What's that? Theta. It's both an upper and a lower bound. Yep. There we go. Okay, so now we can talk about P and NP. P, it's a major unsolved problem in computer science. Informally, when we talk about P, we talk about problems that we can solve quickly. And when we talk about NP, we talk about problems that we have no way to solve quickly, but given a solution, we can verify that quickly. So some examples are like Sudoku, the Sudoku board. If you get a complete board that's already solved, you can check that really quick and be like, oh yeah, that's legit. But if you get a blank board, that's going to be pretty hard to solve. It's actually really easy to solve a 9 by 9 Sudoku, but you make that like 25 by 25, it's going to take 100 years. Graph coloring is another one. Traveling salesman. This is one that people encounter without knowing it. So you've got like 5 salespeople, and you want to send them to 10 cities, and you build a little scheduler for that, and it works great. And now you got 15 salespeople, and you want to send them to 100 cities, and that will never finish. Like same code, same algorithm, never going to finish. This was first formalized in the early 70s, and we've been working on it ever since. I spent 3 years in my grad school experience finding this exact problem. So how's it going? Come on. You can do it. Not very well. We have not made any progress on this problem, one way or the other, in 70 years. In 2000, the Clay Mathematics Institute formulated the Millennium Problems, and they offered $1 million for any progress either way. That prize remains unclaimed. And of course, if you did solve this, you'd probably throw the world in chaos, but that's another issue. We'll talk about it later. And the reason I ask people, when I interview people, the reason I ask them this is the only wrong answer here is the bluff. If I ask you, does P equal NP, and you say, I don't know, that's technically the right answer. If you say, we don't know, that's absolutely the right answer, and I know you have some theory. If you try to bluff, then I know that you're not going to tell me when you don't know something, and I probably don't want you. Okay, Boolean satisfiability and NP complete. Boolean satisfiability is kind of the core NP complete problem. Given a Boolean formula, is there an assignment of truth values such that the entire formula is true? Generally, we talk about 3-sat in conjunctive normal form. So you have a series of OR clauses joined by AND. And you have to find an assignment to all the literals such that the entire clause is true. You can express a lot of problems with that structure, right? Assuming an infinite number of clauses or arbitrarily large number of clauses. And so because of that, if you could solve this problem, you could solve any other NP problem because you can reduce it to this in polynomial time. Nobody's been able to do that either. The Davis-Putnam-Lodgeman-Loveland algorithm, DPLL, is the current best algorithm for this, and it is exponential in the input. I haven't really made much progress on that, again, in about 50 years. So that's most of the math stuff. Any questions or comments there? Any of that land? Okay, moving on. Camera. There we go. So these are the key takeaways. Like if you take anything away from this talk, this is the slide. There's large number of problems. In fact, there's way more problems that are unsolvable than there are solvable problems, even with a computer with infinite time and infinite memory. That's kind of wild, right? When you step back and think about it. Generally, things with sub-exponential time we consider solvable or easy. Most of the stuff that we do on the day-to-day basis are even easier than that. They're like logarithmic time or even linear time. Boolean satisfiability is the key hard problem. Any solution to that we can generalize to any of the others. And then really everything in computer science is a trade-off. Like you're always trading off between one thing or another. Not necessarily. Right. No, so there are problems with infinite time and infinite memory. You can solve some of these problems, but it's going to take 1,000 years. So that's effectively unsolvable. It's not actually unsolvable. It's not undecidable. But within a realistic time frame, it's effectively unsolvable, right? Especially for larger inputs. And that's the key with a lot of these problems is, that's the next slide. Time and space is kind of the primary trade-off. And with or without knowing it, you're doing this all the time. Like a hashing function is trading time for space, right? You're spending your time running the hashing function to take an input space and reduce it down to a smaller space. You're saving space at the cost of time. On the other side, you have a lookup table where you can store a whole bunch of stuff in a flat table and look it up really quickly. Now you're trading space for time. Chinook, which is the first master's level checkers program, and I actually worked on this a little bit in grad school. I got shipped up to Edmonton, worked with the games research group. The way that works is a series of lookup tables. They spent months calculating every possible move, starting from 7 different starting moves. So they had 7 trees. Each of them took like 3 weeks to run. And then they cached that all in a hashing table. And then the program, all it did is it took the board, looked it up in the table, and made the next move. That was all it did, right? And it played perfect checkers because it always knew the right move. Another major trade-off is the clarity of programming languages versus performance. So probably everybody in this room knows C and C++ are much faster. The reason is because you have to manage memory. C# and other higher order languages are slower because they're doing that for you. There's a trade-off there, right? The compilers make that much better, but it's still present. Python's kind of a weird case here because it's an interpretive language, so it's inherently much slower. But because almost all the work's on the database side, they kind of cheat. And that's why all the data science stuff is moving to Python, because it's really easy to write, and they have all these libraries for it. And then clean code versus tech debt. Yeah, it wouldn't be a talk of mine if we didn't talk about clean code at least a little bit. This isn't really fair, but there's definitely a trade-off there, right? If you spend the time to write cleaner code, you will pay for that much less later. And as computer programmers, we spend the vast majority of our time reading code and not writing code. So write code that's easy to read, and that'll serve you well. So identify when you're approaching exponential time. The vast majority of things we do are not close to this. Even like an n-squared algorithm, like a true graph, cross product, is not exponential time. That's n-squared. So when you're getting to truly exponential time, you're hitting something really hard. And again, traveling salesman, Sudoku, Boolean sat, there's a bunch of them. If something works really well on a small input, but then just completely fails on a medium-sized input, that's a pretty big tell that you're approaching this. Takes practice and experience, but having a good understanding of theory will help you get there. And again, most of the time you don't need this. But if you do get yourself into a situation like this and you have to do something, go look for a good algorithm, because there's probably something out there, and it's going to be much better than whatever you're going to come up with, most likely. Okay, important numbers. This is the numbers every programmer should know slide. I think the last update for this was in 2020. It's out on the web, linked at the bottom. It's probably the network is the takeaway. Like, things on chip are really fast. So the first column is nanoseconds. And these are like, accessing a level 1 cache, branch mispredict, stuff on the chip. The second column is blue. There's an order of magnitude shift there. And that's like local memory, RAM. Third shift is writing stuff to disk. Your actual hard drive, again, it's another order of magnitude. And at the end, we get to some of the beginning of the network connectivities. So we're like 3 orders of magnitude slower when we're running stuff across a local network in our office compared to being on the chip. And then one more order of magnitude, now we're talking about going across the internet. So again, almost always the bottleneck is going to be network connectivity and moving data to the thing that you're trying to do with the data, not actually processing the data. Again, there's exceptions, but they're pretty rare. Cryptography. This is one of the cases where all of this stuff really matters. Almost all of modern cryptography is based on this theory. It's some sort of cryptographically hard problem, NP problem, and that's how it works. So prime number factorization is the most commonly used one. This is kind of a weird one because we don't think it's actually NP complete. We think it's in NP. That crazy formula is the best known algorithm. It's still exponential, but only barely so. RSA public key encryption is another one. Discrete logarithms can be used for this too. Hashing functions, all the same. But this is essentially the same as the P versus NP problem. It's very hard to solve 2 prime numbers that multiply to some huge huge number. But it's very, very easy to check those 2 prime numbers multiplied to some huge number. This is how public key encryption works, right there. Quantum computing. This stuff is wild. It doesn't really work yet. They've been trying to build these for a long time. It uses qubits instead of bits. So it's not just a 0 or a 1. Instead, it's electron shells, and you can do multiple operations on a single bit at the same time. I've got a pretty good grasp of like the physics of a regular computer. I have no idea what's going on here, right? Although Satya Nadella in 2017 said that quantum computing, augmented reality, and artificial intelligence are going to be the 3 main technologies of the next decade. And so far, he's been proven we're right on one of those at least, right? If they ever make one of these work, the implications are profound, because you can solve prime number factorization with a quantum computer very, very fast. So that means all cryptography is broken instantly. Everything from your bank account to nuclear access codes, all of it out the window. We do have cryptographically secure methods that run on quantum computers, because a lot of researchers have been looking at this for a while. But they're so expensive to run on regular computers that none of them are in use. So yeah, there's going to be a real ugly transition if they ever get one of these working. They're still a Turing machine. The quantum computer is still a Turing machine. It can still represent it with the same formula. And if they ever do get these working, there's huge potential for advancement, particularly in molecular engineering. Right now, when we try and design new medicines, we basically put together some compounds, see if they're stable, and see if they work. Then we do that again, we do that again, we do that again. Very trial and error. If you had a quantum computer with like 40 qubits, you could just plug it in and see if it works ahead of time, and then go build it. You could do the same thing for agriculture engineering, so like fertilizers and other compounds like that. You could figure out what's stable and what works ahead of time. But again, none of them really work. And that's my talk.